This is a very simple C++ multi-thread program. The initial conditions are A and B are both equal to 0. Then core 1 change A to 100, then change B to 500. Core 2 perform a check on the B value. The while loop will not exit until B reaches 500. Then A is assert whether it is equal to 100. Assume this code runs on any target platform. The question is, does the assertion always pass? If you have heard about memory order, you know that in the multi-thread program, you cannot rely on the program order to analyze the behavior across multiple threads. So the answer for this question is that this assertion might fail on certain platforms. And in this video, I'm going to explain what is under the hood that might affect the memory order in the multi-thread program. When you observe something that is against your intuition, you need to analyze the chain from the head to tail. In this case, the beginning of the chain is the C++ source file. Then the source file is compiled to assembly instructions that runs on a certain CPU target platform. The processor executes the assembly instructions. Then you get the behavior of your program. Actually, the processor is a major part affecting the memory order behavior, so I will start from the processor part. Let's have a short recap of the 5 steps of a very simplified single processor. Step 1 fetch the instructions to be executed. Step 2 decode is to identify the instruction type and the operand that the instructions can be sent to the execution step. In step 3 execute, the normal arithmetic instructions are sent to the algorithm logic units, such as integer add or integer multiply. Beyond that, the load and store instructions are also executed in the step 3. The load means reading the data from the given memory address and save it to the given register. The store means to write data from the given register to the specified memory address. To highlight here, the load and store instructions in the execution step do not really involve the data interactions with the memory, but they do some calculations as well. The address in the operands of store and load instruction is usually the offset address from the register, so that this address needs to be translated to the virtual address and eventually translated to the physical address. Step 4 and 5 involves the read and write of the actual memory data of the registers. For load or store instructions, the data will be swapped with the memory. For the regular arithmetic instructions, the calculation results are stored to the specified registers. In some textbooks, step 4 and 5 are combined as one step, to make sure that you are not lost and confused while reading the different representations of the same stuff. The sequential mode can be drawn in the timeline as either a non-overlapping model or an overlapping model. The overlapping model saves time compared to the non-overlapping model. Both timelines naturally guarantees the computation steps and the memory access in the order of the assembly program order, so you won't have any problems with the memory order in the sequential single-core model. The sequential overlapping model is also known as the sequential pipeline. From this example, you can see that the pipeline stalls to fulfill the data dependency among the instructions. Humans are very greedy about the computation speed and aim to make faster processes. The modern processors employ multi-core, out-of-order execution pipeline and shared memory among the cores. To understand the memory order behavior on these modern processors, let's dig into the architecture. This is an architecture of the single core of Intel Skylake processor. Although it has a lot of different units working together, we can focus on the units that are most relevant to the memory model in the out-of-order execution pipeline. Multiple instructions are decoded simultaneously. After decoding, the instructions are sent to the reservation station. This is a place where the instructions are waiting for their availability of their operands and execution unit. Let's say there is an add instruction and one operand register is not available yet because it is used by another execution unit at the moment. The instructions that cannot be executed at the moment are temporarily stored in the reservation station until the readiness of the operands and the execution unit. The lifespan of the instructions in the execution units do not follow the program order, because the moment every instruction starts execution in the execution unit is out of order to some degree, given the availability of their operands and execution unit. The execution time of different types of instructions, such as add and multiply, is also different, which causes a difference of the duration in the execution units. Regardless how progressive the out-of-order execution can be, the execution result must be strictly the same as if all instructions are executed sequentially following the assembly program order on a single core. The lifespans of two independent instructions can be reordered differently from the assembly program order. Assume instruction I1 is ahead of instruction I2 in the assembly program order, and they are independent with each other. Then the lifespan of I1 can be fully ahead of I2 or fully after I2 or overlapping with I2 in the timeline. If I2 is logically dependent on the execution result of I1, then the lifespan of I2 cannot start until it gets the results of I1. Reorder buffer is a place that contains all the instructions staying in the reservation station being executed in the execution unit at the moment, or those finished by the execution unit but wait to be completed in the program order. Because of out-of-order execution, an instruction itself might be already finished computation from the execution unit, but another instruction preceding it in the original assembly program order might not be finished yet. The use of the reorder buffer is to force all the instructions to exit sequentially with the assembly program order. We can define the term architecturally completed, which means an instruction has exited the reorder buffer. The instructions are finished by the execution unit but have not exited the reorder buffer yet, are not architecturally completed. The reorder buffer provides a sequential architectural completion timeline that is honest to the original assembly program order, and this sequential architectural completion timeline is important when analyzing the memory system. Some other techniques are also used in the modern out-of-order execution pipeline, for example, register renaming and branch prediction. Since they are not directly relevant to the memory order, I will skip them. The out-of-order execution is not the full story of the memory access behavior. To figure out the whole picture, it is necessary to understand how does the load store unit and cache work in a modern CPU. In short words, the load unit, store unit, and store buffer have data exchange with the cache, but they never directly interact with the DRAM. The cache comes into play because the CPU is much faster than the DRAM. I will start from the load and store unit. When the store unit has performed a successful address translation, the register data to be stored to the memory are kept in the reorder buffer. When the store operation is architecturally completed, the address and the data to be stored are pushed into the store buffer. The store buffer stores the architecturally completed store but not yet to be retired to the memory system. In this case, it means the L1 cache. I will use the term retire to refer to the updating of the memory system. When the store operation becomes retired to the L1 cache, the store is removed from the store buffer. The purpose of the store buffer is to allow the stores to be committed to the DRAM when the memory bus is not busy. The load unit does the address translation same as the store unit. Then it has two sources to read the data. One is the store buffer, the other one is L1 cache. The significant difference between the load and store instructions and the instructions without referring to the memory address is the ambiguity of the data dependence. It is apparent that the data dependency between the register-to-register instructions are explicit and pre-known after the instructions have been decoded, while the data dependencies of the memory address of the load and store instructions are not known until the load or store unit has calculated the physical address. The memory address ambiguity introduces a challenge if the load store instructions are not executed in the assembly program order. Different CPU architectures might handle the ambiguity of the memory dependency in different ways. One conservative way is to limit the out-of-order among the load and store instructions, while still allowing the out-of-order of the instructions that do not involve the address translation. In this way, all the load instructions will search if the address to be read matches any entry in the store buffer. If yes, then read the data from the store buffer. If not, read from the L1 cache. The more aggressive way is to allow fully out-of-order execution of the load and store instructions, but with some correction mechanism. Remember these rules about the reservation station. The instructions architecturally completed have exited the reorder buffer. The instructions have been executed but not architecturally completed stay in the reorder buffer. The reorder buffer exits each instruction strictly as the assembly program order. The load and store instructions start in the execution units out of order, even if they might have a memory address dependency. The load instructions calculate the address and read the data from the store buffer if the address alias is detected, or load from the L1 cache if the address alias with the store buffer is not detected. The loads are speculative. They reside temporarily in the finished load buffer after the address translation and data fetch, until architecturally completed. Whenever a store instruction is being architecturally completed, it must perform alias checking against the loads in the finished load buffer. If no alias is detected, the store is allowed to complete. If alias is detected, it means that there is a trailing load that is dependent on the store, and that load has already finished execution. This implies that the speculative execution of that load must be invalidated and corrected by reissuing or even refetching that particular load and all the subsequent instructions. In fact, there are different rules about how aggressive the out-of-order execution of the load and store instructions can be in different CPU architectures, as long as the execution results are logically correct. The CPU cache is a small buffer between the processor and the DRAM because the memory access speed is much slower than the processing speed in the CPU. In most modern CPUs, each core has its private L1 and L2 cache, and all the cores share the L3 cache, which connects to the DRAM. The entry of a cache is called cache line. Each cache line maps to a chunk of 64 bytes in the physical address. The 64 bytes physical address chunk can have one copy in one core, or several cores have such copy. When the load or store operation attempts to read or write data in the memory, the cache controller of this core receives the request. Then the cache controller calculates which 64-byte chunk is requested. Then the cache controller checks whether the L1 cache contains a clean entry of this requested chunk. If a clean cache line is found, we call it a cache hit. Otherwise, either the cache line does not exist in this private cache, or it is marked as dirty, which means the data of this cache line has been updated by the other cores. A cache miss occurs. When a cache miss happens, the cache controller either requests other cores to provide the most fresh cache line data, or requests from the DRAM. In a multi-core processor, different cores might write to the same address. Then a consistency problem comes when another core attempts to read that address. What value should be read? Consider a simple scenario involving two cores, Core 1 and Core 2, a shared memory location X, which initially holds the value 0. At the beginning, the DRAM contains X equals 0, and the caches for Core 1 and Core 2 do not have a copy of X. Then Core 1 attempts to read on X. It fetches the value 0 from the DRAM and stores a copy of that cache line containing X in its private cache. Subsequently, Core 2 also reads X, fetches the value 0 from the DRAM, and creates a copy in its own private cache. At this point, the DRAM, the Core 1's cache, and Core 2's cache all hold a consistent value of x. Then Core 1 executes a write operation, change the value of x to 100. This update is only performed on its local cache line copy. The memory system is now in the incoherent state. The Core 1's cache holds x equal 100, while Core 2's cache and the DRAM still hold the obsolete value x equals to 0. If a third processor, Core 3, were to read x, the value it receives will be ambiguous. If it reads from the DRAM or the Core 2's cache, it gets 0. If it reads from the Core 1's cache, then it will get 100. This non-deterministic behavior is an incoherence. Due to this, an abstract model regulating the behavior of the cache axis and the DRAM axis that can avoid the inconsistency of a particular memory address is necessary. Such a model is called the Cache Coherence Protocol. You might have heard of the MESI protocol or different hardware implementations of the Cache Coherence Protocol. The details of them are out of the scope. Regardless the protocol and the implementation, the cache coherence can guarantee two things. Number one, the write of one core can be eventually propagated to the other cores. This means if a Core 1 writes a location x, any subsequent read of x by another Core 2 that is sufficiently separated in the time must return the value written by Core 1, assuming no other writes to x have occurred in between. Number two, all cores must observe the write operations in the same memory location in the same order. If a location x receives two different values, first value A, later value B, from any two cores, no cores in the system can ever read the value of x as B earlier than the read of value as A. All the cores must observe the sequence of values as A, later B. In other words, cache coherence requires all the cores to get the same observation of the modification order sequence of the same location x. However, the precise moment when the core becomes aware of a value change might be different from another core due to the transaction latency. The important notice is that Cache Coherence Protocol cannot enforce each core has the same view on the modification order of different memory locations. Assuming two memory locations x and y at different cache lines, the Core 1 writes A to location x, then Core 2 writes B to location y. Some cores might observe the modification of x earlier than y, some vice versa. This is a basic fact you have to remember when analyzing the memory access behavior in a multi-thread program. After long talking about the reservation station, reorder buffer, load and store units, and the memory system in a modern processor, we can go back to the example in the first slide. I have simplified the C++ code to the assembly code. The right side shows one possible timeline when Core 2 reads B equals 500 and A equals 0. For each core, the instructions are architecturally complete in the assembly program order. The architecturally completed stores reside in the store buffer and wait to be written to the L1 cache when the memory bus is not busy. If the write attempt at address A encounters a cache miss, and the write attempt at address B encounters a cache hit, the write at the address B have a chance to be committed to the L1 cache earlier than the address A. Then, when Core 2 attempts to load the values at address A and B, it might get the combination B equals 500 and A equals 0. In summary, the overall behavior of out-of-order execution, load and store unit, and the memory system defines the hardware memory model. Each core is guaranteed to observe a unified modification order of the same memory location, but no guarantees on a unified memory modification sequence across different memory addresses. Beyond the hardware memory order model, the compiler also plays a role that affects the memory order. For C++ developers, you are responsible to understand the hardware agnostic memory order defined by the C++ standard, which is a contract between you and the compiler. The compiler has freedom to do some reordering and optimizations as long as the execution result in the single thread is not changed. The compiler shall also guarantee the memory order behavior in the C++ source code can be correctly translated to the assembly code of the target platform. Here is a table shows how the atomic functions in C++ with several memory order can be translated differently in the x86 or ARMv8 platforms. This table is also an evidence to show that the hardware memory model of ARMv8 and x86 are different. We can also get another important conclusion. The C++ memory order defines the strongness of the programming language can guarantee on every target platform. The compiled assembly code on a specific target platform has at least the same strongness as the C++ standard requires, or even stronger memory model. The move instructions on x86 can satisfy the C++ memory order sequential consistent. It is also used within non-atomic instructions and relax or acquire atomic instructions. This is the end of the long talking. I hope you have a better understanding regarding the memory order, both in the hardware level and programming language level. Thank you for watching until the end. See you next time.